Hello everybody. In the last class we had seen how Moore model and Mealy model are defined and what are the relative advantage, disadvantage. Then we picked up one specific problem statement and we tried to solve that problem using both Mealy model and Moore model, and in the process we understood their relative strength and weaknesses. And in this particular class, so we shall move ahead with that problem statement, and we would like to see how the circuit is finally realized, and we shall look into another part of the comparison, that for the same problem statement, the circuit that we get from Moore model and the circuit we get from Mealy model, how do they compare in terms of complexity. Okay. So, we continue with the problem. You are aware of that problem. The problem was that of detecting a sequence from a binary data stream, okay, and the sequence to be detected was 1 1 0. Okay. This we remember, right? And for that, the Moore model, we had the circuit, we had the state transition diagram, something like this, and the 4 states were defined in this manner, that A, that is the initial state, no bit is detected properly, B, 1 bit is detected, okay, C was 2 bit detected and properly, and D was all 3 bits have been detected properly. Okay. So, that is what we had defined in terms of the states, right, and we had seen that when it is at A, 0 is there. So, basically it is remaining at 0, 1 it is going to B, again at B, when it receives a 1 it goes to C, that means 2 bits are properly detected, and then when it is receiving a 0 it goes to D, 3 bits are properly detected, and it is a Moore model. So, output is generated solely from the state value. So, at D the output is shown, and the rest of the cases, other options other than these different sequences, they are in the other path that you see in the state transition diagram. Okay. So, this we have discussed in detail in the previous class. Okay. So, you can refer to that. Now, we need to see how the circuit is realized. So, for that we need to do a state assignment, because states we have mentioned in terms of A, B, C, D, right. Now, we have to refer to it in terms of the memory elements. So, we shall be using flip flops. So, in terms of the flip flop values, right. So, how many flip flops will be required? So, there are 4 states, right. So, from this formula, that ceiling log n to the base 2, where n is the number of states in the state transition diagram. So, by which we can see that 2 flip flops will be required, okay, right. Ceiling means if it is a fraction, it will be taken to the next higher integer. Okay. So, if it is 1.2, it will be 2, okay, 2.3, it will be 3. So, that is the meaning of this particular operator. Okay. Now, so these 4 states, so A, B, C, D, they need to be associated with 2 flip flops, 4 different values. Okay. So, one option is the standard one, A, the first one it is coming, so 0 0, B is 0 1, C is 1 0, D is 1 1. Okay. This is the way you can do the assignment, and then move ahead with the circuit realizations, right. But there could be alternate way of doing things also, right, and which one will give a simpler circuit, less complex circuit, in the sense that less amount of combinatorial hardware and all, number of flip flops remains the same. Okay. So, that is something cannot be told in advance, okay, that need to be worked out and see, because one more assignment could be that only one flip flop, A, B, C, D it is there. So, only one value, one flip flop value changes as we move from A, B, C, D. Okay. So, that could be one thing. So, only one flip flop value changes. So, we can guess that the requirement for changing and the complexity related to this combinatorial circuit, they may be less. Okay. So, in that sense we can assign 0 0, then B is 0 1, only one value is changing, C is 1 1, and then D is 1 0. Okay? And from D, if it goes to A, it is again going to 0 0. So, in that sense that could be another way of assigning it, but one need to be careful. What I have shown here, that you can see from D it is going to B as well as A. So, in this assignment when it is going from D to A, 1 0 is changing to 0 0, so one value, but from D when it is going to B, so 1 0 is changing to 0 1. So, both the values are changing. Okay. So, these are the things because of the interconnection. So, that is why I said that you need to see it in detail, and many different things are there. Otherwise, we can move ahead with any one of them and realize the circuit which will work. Okay. So, we consider the first one, okay, but you can try as an exercise that how it would look, how the circuit will be appear then with this assignment. Okay. So, that you can take as an exercise. So, after that what do you do once the assignment is done? So, the state transition diagram now we can present in this manner. Okay. So, 0 0, right, then 0 1, 1 0 and 1 1. Okay. And let us consider we are using JK flip flop for its realization. So, then we shall figure out what is the JK flip flop excitation table. From our earlier class we know that JK flip flop excitation table is this one. So, 0 to 0 transition, 0x, 0 cross, that means 0, k can be 0 or 1, any value, right. For 0 to 1, 1 cross, 1 0 cross 1 and 1 1 cross 0. Okay. So, this cross here is do not care, that means any of 0 or 1 will do. Is it fine? This we all know, right. So, then if we move ahead, so if we try to see it, we go to the state table, right. So, this is the present state, okay, and now the input is here. So, you have to consider present input as well, right. If you have seen that synthesis of counter design problem, there we did not consider the input, right. So, it was moving from one state to another with the clock getting triggered, okay. And then next state, okay, and the output will be generated solely from this present state values, right. And for this there are two flip flops, so the corresponding flip flop inputs. So, these are the different columns of the state table. Is it fine? So, for 0 0, so 0 0, so we are showing it in one block, right, the current state. So, input can be 0 or input can be 1. Is it fine? Right. And in that case for 0, next state is what? 0 0 only. From the state transition diagram you can see 0 0, right. Okay. And for 1, it is the next value, that is 0 1. We have already done the assignment. Earlier it was A and B. So, now it is 0 0 and 0 1. So, this is 0 1. Okay. So, if it is 0 1, then there could be two possibilities, 0 and 1 for the input. 0 1, with 0 it goes to 0 0, with 1 it goes to 1 0, right. With 1 0, this one, again two possibilities, with 0, okay, it goes to 1 1, right, and with 1 it remains at this place. So, this is at 1 0, fine. And finally, for 0 1, sorry, finally for 1 1, right. So, we are here, for 0 it goes to 0 0 and 1 it goes to 0 1. Is it fine? So, once we are done with this, then the rest is to take help of this excitation table, and for each of this transition Bn to Bn plus 1 and An to N plus 1, write down the corresponding JB KB and JK, the input that are required at respective flip flops. Is it okay? So, 0 to 0, 0 cross, sorry, 0 to 0, this is 0 cross, 0 to 0, again 0 cross, 0 to 0, again 0 cross, and 0 to 1, okay, 0 to 1 we know this is 1 cross. So, this way you can complete it. Is it fine? Right? So, this is that column. Now, what about the other thing? So, this is your an to n plus 1 that we have to consider. So, 0 to 0, 0 cross 0 to, this is 1, 1 cross we have already seen, 0 to 1, then 1 to 0, 1 to 0, this is 1 to 0, this is cross 1, right. So, this is cross 1. Okay. So, that is the way it will proceed. Is it fine? Right. So, this is this particular column that also you get. So, what is left now? This output, how we fill up this particular output. So, since it is Moore model, right, output is always generated from the state, does not depend on the input. Okay. So, irrespective of the value of the input, so basically input is a kind of do not care in this condition. So, you do not bother, it will be totally derived from the state value. Okay. So, when it is at state 0 0, okay, for either of these options the output is 0, 0 1 0, 1 0 it is 0, and when it is at 1 1, okay, current state, then the current output is 1 1. So, that is what you see over here. Is it fine? So, with this we are able to complete state assignment, then corresponding state transition diagram with assigned state values, okay, in terms of flip flops, then state table using the help of excitation table. So, next step will be, as we had done in the past, is to get the corresponding this simplified relationship for these two flip flops. Okay. So, those are the design equations, right. So, that you can get. So, what we need to do? We need to just map it, right. So, three variables are there, the current state and the current input, right, and what will be the current input means input bit that is coming from here. So, this current input for the flip flop for which the next state is defined. Okay. So, in a particular manner as far as the state transition diagram is concerned. Okay. So, in that way we are just mapping it from the state table over here, and once we do that, right, for JB, once we map it in this manner, if you just, for example, we take up 1 and the rest can be, so for JB 0 0 0 1 cross 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 cross, is it okay? So, let us look at it. Okay. So, this is 0 0, so 0 0 0 1, okay, cross 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 cross, okay, 0 0, then we had gone in this direction for 0 0, this was the 0 1 for x 0 value and x 1 value. So, this is 0 0 0 1 cross cross and this is cross cross, right. So, similarly you will be mapping the other things, and then you will be getting the largest group of in integer power of 2, all those things the Carnot map based simplification. So, by this you get these 4 equations, right. And in this case what you get? In this case you do not need the consideration for x, because it is solely derived from state value. So, state values are like this a n and b n, right. If you put together, when both of them are 1, it is 1. So, y is equal to a n b n. Is it fine? So, with these design equations in hand, okay, we move to implement the circuit, right. So, these are the equations that has been taken from the previous slide over here, right. So, these are the two flip flops J A and K are the inputs for flip flop A, J B, K B for flip flop B, right. And you can see this is your input X, is the clock synchronous circuit, clock is triggering both the flip flops simultaneously. So, J B is X A N. So, just to verify some of this thing. So, J B is this one, right. So, X A N. So, this is your A N over here and this is your X. So, you can see that X is coming like this, this is the connection and this is the other one. So, this is your X A N and K B is A N. So, K B is A N, you can see that K B is A N. J is X bar B N plus B N bar. So, J B, okay, sorry, that is J A. So, that is your J A. So, you can see that X bar. So, this is your X bar, right, and this is your Bn. So, this input, this is your x bar, and this is your Bn, and this input is your x, and this input is, it is coming from here, you can see it is Bn. So, that is J, right. K is x bar plus Bn bar. Okay. So, this is the OR gate. So, x bar is here and Bn bar is coming from here. So, you can see the feedback, right. And finally, your y is equal to a n Bn, right. So, this is y. So, Bn is here and an is here, right. So, once the equations are there, design equations are there, even if it looks a little bit complex, we are in a position to get the corresponding circuit. Is it fine? Right. So, this is Moore model based circuit for that 110 detection. Now, we go to the Mealy model based state transition diagram and its realization, right. Now, one thing that we notice first, that number of states are 3, okay, because when 2 bits are received correctly, okay, 1 and 1, then if 0 is received, okay, in that same clock cycle we can generate the output, okay. So, that is the thing, right, that is the Mealy model. It can give the output based on current state as well as the current input, okay. So, that we discussed in the previous class. So, that is how it looks like this, right. So, that is why 3 states are sufficient, right, for this problem. So, this 3 states, then how many flip flops will be required? Of course, 2 flip flops will be required, that because of this operator, okay. It is one flip flop, with one flip flop you can have 2 states only, okay. So, 3 states are there. So, state assignment, so let us do it this way, A is 0 0, 0 1 and 1 0, okay. So, again for state 0 0, 2 possibilities 0 and 1, 0 1 2 possibilities 0 and 1, and 1 1 2 possibilities 0 0 and 1, right. And accordingly the state changes are taking place similar to just Moore model, right. So, 0 0, Ty we had prepared the state table. So, 0 0 it is 0 0, 0 0 it is 0 1 for 1 here, 0 1, 0 1 it is going to, for 0 it is going back here. So, 0 0 this is going to 1 0, for 1 0 if it is 0 is received, okay. So, 1 is the output, you can see the corresponding output is 1, right, and next state is 0 0 and 1 0 it is 1 0, okay. So, present input, now the difference, that when it is at 1 0, this is C 1 0, right, when it is at 1 0, if it receives 0, okay, it is 1, and if it is receives 1, it is 0, okay. So, under this condition only the input output is 1. So, this is the difference, right. And the way we had filled up the JK flip flop input columns in Moore model, the same thing we will do by using the JK flip flop excitation table. So, that has been shown here, okay, and you can do it yourself also, right. So, what is the other difference that you can see compared to Moore model based state table, other than this X is contributing to Y generation? Other than that, what you can notice, that one pair of column is missing, okay, that is 1 1 is not there, right, because state D is not available or not required, okay. Now, how does it help in circuit realization? Does it help in any way to reduce the complexity? So, let us see. So, this we have noted, right, and again we note down one particular case, like say this one, JB KB is 0 0 0 1 cross cross, okay. So, that we had seen before, that JB was also cross cross here. So, we will not be able to, so other cases cross cross 1 0, okay. So, let us see one such case where we had this one, okay, KB cross 0 0 1 1, right. So, now we need, in this particular case, KB, so we have in this particular case just by comparison. So, this one JA we are talking about 0 1 cross 1 0, then there was cross 1 1, sorry, KB cross 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 0 0 1 1. Okay. Okay. So here it is different because it is going from 0 0 to 1 0 to 0 0. Okay. So that's why it is cross 1. So what you can see now for this KB, right, over here. So this 1 1, earlier it was 1 1, right, but here you can see that this is cross cross. For KB it was 0 0 because the state change was different. So that is another aspect of it, but this 1 1, okay, was not cross cross, was 1 1, right. For JB it was cross cross because of the way the next state values were there, but at least over here you can see that 1 1 is not there, it is cross cross, okay, because 1 1 is not coming, this state D is not coming into picture, right. So similarly over here, right. So for which it do not have any requirement as was the case in the other mood model based realization. So if there was a 1 here, that 1 need to be covered. Okay. So since it is not there, so you don't need to cover it. So that way you can see the final equations that you get are simpler than the one that you had seen in case of mood model, right. So because of which you will be having, at least for this part, a relatively simpler circuit, isn't it? Okay. But one thing that we note here, that there are only 2 such variables were there. Now we have got 3 variables coming into place. Okay. But even if 3 variables are there, the circuit that you have is, the logic is, earlier it was AN BN, now it is X bar BN. So that way it is not making too much difference. Okay. So and X, for other reasons, there is X bar is always getting generated because of the NOT gate. Okay. So even if it is not getting generated, then only one additional NOT gate is required, other than what we had seen before, the AND gate required for the mood model. Okay. So this is minimal, even if something, because of this additional variable that is there. But in the other cases, you can see that there is a relatively less complex design equations that we get because of the state D not being present here in the Mealy model. Okay. So with these equations, now you can see these are the equations, right, and in the other case, if you remember, for J it was x bn bar plus x bar bn, some such thing, isn't it, right. So you can see that all those things have got simplified, I mean more simple. Okay. So this is the for the same problem you have got a Mealy model based circuit like this. So usually because of less number of states being there, and possibility of having don't care and all, so you can see, you can expect that more complex circuit will be for mood model and less complex for Mealy model. Is it fine? So before we end, we would like to extend this thing on the complexity part, but by bringing another example, which is in a sense extension of the previous example. So we shall have also a practice of developing Mealy model, mood model. So let us see. So this is a sequence detector problem only, as I said, extension, but it is now what we want to be detected is 1101. Okay, earlier it was only 110, so one more bit has been added. So whenever these 4 bits 1101 is found to be present in the input data stream, we say that the sequence, that sequence we were looking for, that has been there. Okay. And the other thing what has been mentioned here, that overlap is allowed. Okay. So what does it mean? After 1101, okay, if it is non-overlapping, that means you need another 1101. Okay. And if it is overlapping, that means after 1101, again if you get a 101, this one is getting included. So that is the overlap. So then also you will say here there will be one output, again here there will be a one output when you are over here. Okay. So, that means if it is overlap type, then final bit or bits of a sequence can be start bits of next sequence. Okay. So, that is the thing. So, let us see if such is the case, how it would work out. Okay. So, we start with a Mealy model. Okay. The same thing that the way we have defined. So, A means no bit has been detected properly, B 1 bit, C 2 bits, and D 3 bits. Now, we need 3 bits because 4 bit is to be detected. So, when you are at D, that means 3 bits have been detected properly. Okay. Then based on the input you take a decision. Okay. So, that is the requirement. So, at A, so initial part will be similar to what we had in the previous case, because it is 1 1 0 the first 3, right. So, A 0 is received, it is staying here, A 1 is received, it is going to B because it is 1 bit properly detected. So, it receives another 1, second bit properly detected, it comes to C. Okay. But after 1, if 0 comes, then again you have to restart up. Okay. So, that is why for 0 it is going back to A, right. Then at C, if you receive a 0, that means 1 1 0, 1 1 0 has been received. So, you come to, that is 3 bit correctly received. So, you come to D, right. And if you receive a 1 here, you stay at C, because after 1 1 you can, if you get a 1, again if you get a 0, then you are doing right, that is you are going right in the detecting the sequence. So, you are staying here at C. Okay. Now, when you are at D, okay, 1 1 0, then if you receive a 0, what happens? Okay, you have to restart the entire thing, isn't it? So, that means again you need to look for 1 1 0 in the incoming bit stream. Okay. So, that is what has been shown here. But if you are at D, it is 1 1 0 and you receive a 1, okay, then mean it is correctly detected, right. So, the output will be 1, that is what has been shown here. Now, when this output is 1, after that where the circuit should go? Okay. The circuit should go to a state which says that 1 bit is already detected properly, because after that if you get 1 0 1, which is, then that is you are doing right, okay, because of this overlapping. So, after D with a 1 it is going to B. Is it fine? So, this is your Mealy model based circuit. So, 4 states are required. Now, what happens to Moore model based circuit, right? So, up to 4 state, 3 bits detected. Now, you need another state, okay, which is 4 bits detected, because the decision is taken from the state value only. Unless it reaches E, that means 4 bits properly detected, it cannot generate the output. Okay. So, then if you quickly follow, so it is going A, B, C, the way you have seen before, right. When it is at D, okay, if it receives 1, it goes to the 5th state, that is E, and if it receives 0, it goes to A, because of the same reason the way we have said the bit pattern unfolds. Okay. And when it is at E, okay, then it is at E means it has received 1 0 1 1. Okay. This is already received. Now, when it is at E, it can receive a 0 or 1. If it is receiving 0, then it has to restart, that we know. But if it receives a 1, okay, what does it mean? What does it mean? Right, that 2 bits are properly detected. Please understand this part. 1 0, it is at E means it is already 1 0 1 1, right. Then it is receiving a 1. So, that means 2 bits are properly detected. If you receive another 0 1, then the sequence is there. Okay. So, 2 bits properly detected is your C. So, it is going to C. Is it okay? This part is understood. Okay. Why? Where it is going to B, it is going to C, right? Because after D, that means it is C. It has before that it has received only 0. Here at E means it has received 1. After that it is receiving 1. So, 2 1s are there. Okay. So, and it is overlapping, is it clear, right? So, the other thing that we can see that there are 5 states, okay, and here are 4 states. So, number of flip flops required will be again by that formula. Here it will be 2 flip flops will do, but here 2 flip flops will not do, you will be requiring 3 flip flops. So, it is not only the commutative logic circuit, there could be cases where the number of flip flops, memory elements also need to be more when you compare Mealy model and Moore model. Okay. So, this usually happens in situations like this when you are just moving from one particular case like 4 to 5, so at the junctions. Okay. And finally, on this particular slide, if you are using those conversion rules, okay, Mealy model to Moore model and all, okay, that we had discussed in the last class. So, which one here, I mean, need to be split, because it is, for other cases it is okay, every other case is fine. So, you can see that for that, finding that candidate, we have to see that a particular state at the input of which there are outputs 0 as well as 1. If it is only 0, there is no issue, we can absorb that 0 or 1, okay, within that particular state, right. So, for example, say B, okay, here this output is 0 and this output is 1. So, the B need to be split, okay, B need to be split. So, one B remains here like this, another B becomes E. Okay, you can employ that rule and you can see for yourself as an exercise the way we had done for one example there in the last class for 3B detection. The same thing over here, you can see that if you split, it will be B and E will be coming here, right, and the rest of the cases are fine. Okay. For example, say A, this is 0 and this is also 0. So, you can put a 0 inside. So, none of the other cases there is any such issue, only for B there is the issue, and if you just need to follow the conversion rule and you can do it, and you can come from this side to that side also, I mean Moore model to Mealy model also. Okay. Whenever you see that from a particular place you are having a zeros and ones. Okay. Right. So, to conclude, so we have seen that the to move from the state transition diagram to a particular circuit using Moore model and Mealy model, and this is a finite state circuit or finite state machine. So, often it is called Moore machine and Mealy machine. Okay. So, number of flip flops required will be defined by the number of states that is there. So, it is log to n, the ceiling of log to n. Okay. And assignment of states is something by which one can get 2 different realization of the circuit. Okay. I mean, if you have 2 different assignment, 2 different realization, and one may be simpler than the other. Okay. And from after the assignment, you are going for state table using the excitation table of the flip flops with which you are trying to realize the circuit. We have seen the example of JK flip flop. We could have used SR, T, D, okay, and corresponding excitation table would have been used. Okay. Mealy model, we have seen because of the possibility of having more don't care states, the commutative circuit, that complexity may be less, and also the number of flip flop required may be less in certain cases. Okay. But what we have seen that we have noted from the last class also, that the input is connected to the output logic circuit, the commutative logic circuit. So, any change in the input directly passes to the output. Okay. Thank you.